shuffling through papers. Ah, there we go. Good, thank you. Okay. Now, let me even turn on the projector. Now, I'm moving kind of slowly today. I always move slowly. Even worse. Over the weekend, I was mowing down in sort of a wooded type area, and it was on a downhill slope, and a lot of leaf mulch and stuff like this, but I was trying to knock down some of the poison ivy and other stuff that was growing there. And I happened to run across a yellow jacket nest. And of course they found me before I realized I had found them. So I was trying my best to get up the hill, bringing the mower with me, uneven up a hill, them stinging me like crazy. You got to abandon the mower at that point. No way. Then I was going to have to go back and get the mower, and it's sitting on top of a yellow jacket mound. So I said, no, I'm going to take it with me, so I don't have to come back down here again. So I was swatting at them and trying to pull the mower up and getting uphill, and in all that, I hurt my knee again. I had strained it earlier, and I re-injured it. I don't even know what I did. I may have twisted it. I may have hit the hole. I don't know what I did. I was just trying to get away from the yellow jackets. I got stung at least 4 times, and then my knee was hurting like crazy. I still had to finish mowing, so it was not a pleasant time. So anyway, I'm moving a little slowly today, and especially standing up doesn't hurt, and generally sitting down doesn't hurt. It's just getting in between the two of bending the knee and putting the weight on the knee, either going down or coming up. Neither of those is very pleasant. So I'm moving a little slowly, really slowly. So let's, where we left off last time was here in the very end of 11.2. But because there's 3 more examples to do here, I wanted to be in the section, even though there's no slides for them, so I can go back and refer to the places they are doing. So let's start from here. Let's start from here. Okay, there we go. And we'll do, it's listing 4B, but we've already done 4B. We're going to do example 5, but this is the page we'll do it on. But that's where we'll begin in a minute. Let's talk about where we are right now. Now, I think I've returned to all of you what you've turned in so far of Test 1 and or Test 2. I don't recall how many of you have gotten your research papers, but those are due today, by end of business today, and I will be here today until 6 o'clock this evening, okay? So I will take those anytime today, preferably earlier rather than later, but if you got them, I'll take them. Also, I'll return your other papers to you before you leave today, Corbin. I already have been through the stack, so I don't want to go through it again until the end of class, because others may be coming in too. Okay? If you haven't turned in Test 1 or Test 2, I need those today. I think most of you have turned in those. I'm preaching to the choir here because y'all have generally gotten everything in. Okay, so we're going to cover as much as we can. Today's the last day of class. We're going to cover as much as we can in Chapter 11. And then when we get to the end of the period, I will give you your last test. Just Test 3. Because it's the last test, that's technically your final. I have to hang on to that one because they ask us to hang on to finals for 3 years. I don't know why, but they do. So I will have that for, I won't be returning those to you. If when you come in to turn in your final, you want to get the papers you may have turned in today, I'll give those back to you. Now, not your research papers. Research papers I have to keep again for about 3 years because they periodically ask for samples of student writing. Yes?
Do you know for transient students, like in order for the credit to move over to Auburn, will I have to get you to sign something, or will I just need to get a piece of paper for this class to transfer?
Okay. What you do is request a transcript. Okay. And I think you can do it before you leave here, right? Yeah, go down to the
Request
records office
come back.
and do the pay. You probably can do it online too, but I would check at the records office.
You can do it online.
Yeah, and if they let you do it down there, then you know they have it in their hand, and then when the grades get in, they automatically send it off or wherever.
Because I can't get in my Blackboard or whatever.
You can't?
Yeah, right now we can't. You know, let us check anything.
Okay, now that's the that's student suite.
Yeah, it's students weeks.
Even
Yeah.
like last week, though, right?
Yeah.
What's that?
Last week, like I couldn't even get it.
In Blackboard?
Yeah, I had to get somebody to send me the directions for the paper so I could get on and see it.
Okay. How about the rest of them?
I do the same thing.
I get it.
You can get in. Okay. I know that there have been some times when Blackboard has had problems or our server has had problems. I don't know. I think that's all fixed now. I haven't been on it today, but you say you're on it now? Okay. Okay. So it should be able to get to it now. Now, before I go any further, let me not forget this. Have you done the student course evaluations? Yes? Good. Okay, please do those before the end of the term. I think they keep it up through the end of finals and probably a day or two past that, but look, I remember, even though it's a long time ago, I remember when I was an undergraduate, boy, when that last final was through, it was sort of like, you remember the old Etch-a-Sketches? Shake them and they all disappear. That was pretty much it. It was out of there, you know. So I didn't think about anything else till we got back to the next term. So please don't forget about student course evaluation. Do them while you're thinking about it, but they will be open to you at least through the end of finals. But don't put it off if you're going to forget it, okay? So do it. So I will be giving you your final exam today before you leave. So if by chance you haven't, and by the way, I did put it out on Blackboard. Do y'all see that too? Okay. But if you want a paper copy, I've got it here. Okay. So if you are having to leave early today and not sure you'll be able to get it off Blackboard, be sure you get a paper copy before you go. All right. Now, when's it due and when am I available? Today is the last day of class, and Preston's here. And by the way, I've got your earlier tests graded before you leave today. Pick them up. I've already been through the stack, so I don't want to go through it every time someone else comes in. So I have that. So once I give your test to you, they're due sometime this week, which is today, tomorrow, Wednesday, or Thursday. The college is not open on Friday. I checked on that. But even if it was going to be open, I'm not going to be here because I got a treatment this Friday. So I won't be, but the college is not open. I checked on that and found out it's true. Grades are due by noon on Monday, which means I can't be accepting papers on Monday morning at 10:45. I won't have time to get them graded, put on Blackboard, and put on the faculty suite. So please get me everything this week if possible, okay? Otherwise, you'll be getting an I, and that won't transfer to Auburn or anywhere else. So get me your stuff by the end of this week. Now, as soon as you get me the stuff, if you do get an I, I'll grade it and then change the grade, and then you can get your grades. But guess what? Monday is also our last day here, a week from today. I'm not going to be here Tuesday and on, so I won't even see it if you turn it in after Monday. I will not see it until I get back at the beginning of fall, so that I will not change into a grade because I won't even see your paper. Okay, so please get me your stuff this week if possible. Okay, where will I be this week? I'm here on this campus. Once this class is over with, I'm here until 6 o'clock. My office is down. Anyone not know where my office is? I'll be glad to point it out to you on the little floor plan up there. Everybody knows where it is? It's room 265. And the numbers in this building are rather strange, so let me point it out where it is. Here's our classroom right here in this corner. You go out in the hall, angle out, go down this little half flight of stairs right there, go almost to the end of the hall. basically how the numbers go here, 255, 257, 259, 261, 263, and my office is 265. On the other side is wacko. This is 254, that's 256. Nowhere close. So don't pay attention to the right-hand side. Just look to the left and you'll get to my office in 265. Okay. So, today I'll be here till 6. Tomorrow, Tuesday, my first 2 classes have take-home finals just like you do. So I'll be in the office from 7:45 in the morning approximately until noon. Now at noon, I've got a final in this room, and it'll be approximately noon till 2. I don't think it'll take them that long, but I'll allow them at least that long, noon till 2. Okay? After 2, and maybe even before 2, I'll be back in my office until 3:30. At 3:30, I'll leave and go to the Birmingham East Campus because I have I've given them a take-home final too, so they'll be delivering those anytime between 4 and 6. So I'll be over there. It's the Birmingham East Campus. The building is called the Ethel Hall Health Professions Building. And when you go in the door, it's an L-shaped building like this. When you go in the door at the vertex here, don't go down this hall, go down the left-hand hall, and you walk right past restrooms, and the first classroom on the left is 103. So Ethel Hall, room 103. I'll be there from 4 to 6. And I won't be in class. I'll be teaching, I'll be grading papers or doing emails or something, but I'll be in that room from 4 to 6. Okay, that's Tuesday. Wednesday, I'm here all day long. No finals. I'm here from 7:45 until 6 o'clock in my office, room 265. If I'm not in the office, I'm just out in the restroom or have to go to the registrar's office or something like that. For instance, already today, in between class, one reason I was a little late getting up here, in came someone and said, "You need to help me register for fall classes." I said, "Well, no, I've got a class coming up in 2 minutes, and I can't do it now." So he's coming back between 2 and 6, he said, today. So I'll be maybe registering students, taking them to show where the classes are, where the bookstore is, where the cashier's window, so a lot of new students are going to be around. So if I'm not in my office, if you don't want to wait for me, slide it under my door, 265. Do not slide it under this door. This is a classroom door. Anyone can come in here, pick it up, or the janitor sweep it up, or whatever. So don't do it under this door. Make sure it's 265, my office. You'll see my name and everything on it. Okay, that's Wednesday, 7:45 till 6 o'clock. On Thursday, just like Tuesday, except there's no final. So I'm in my office from 7:45 until 3:30. 3:30, I leave to go to the Birmingham East Campus. I'm there from 4 to 6. Okay? After that, I'm not here again until Monday morning. Now, if you come and deliver, and I've already left the Birmingham East Campus, don't sweat it. Just slide it under my door. When I get in Monday, I'll grade it, and I have time from 7:45 until noon to get things done. I don't have time from 11:30 till noon to grade it and get things done. So have it in under the door, the very latest, so when I come in Monday morning, it'll be there. All right, any questions? For those who came in late, please do your student course evaluations. All right, any questions on anything we've done so far in here? We're right at the end of 11.2. And let me just remind you what we just said, the last things we were working on. Let me scroll back just ever. Definition of parallel vectors. Two non-zero vectors, u and v, are parallel when there is some scalar c such that u is equal to c times v. Okay, that wasn't what I was looking for, but that's true. But I think we can still use it. Okay, let's go on to example 5. Okay, we already did 4b, so let's pick up with 5 now. Okay, determine whether these points. Here's a point P. That's 1, -2, 3. Point Q is 2, 1, 0, and R 4, 7, negative 6. Okay? The first thing to do is determine whether those 3 points are collinear. Now, how would you go about doing that? Determining whether they're collinear or not. Hint, two non-zero vectors u and v are parallel, which also means sort of very close to being collinear, or having same slope anyway, when there's some scalar c such that u is equal to c times v. So what would you do to determine if these are collinear or if they have the same slope? Say that one more time. Okay, these are points. Find the vector represented by those points. So you name a vector from those 3 points. PQ, okay? Let's do vector PQ. And what would that be? And I like to put it in component form. Okay? This aerial. Okay. Okay, before you go, be sure to pick up your papers that I've graded so far. And research papers are due in today. I can't remember. Have you already done yours?
I finished that.
Okay, I need it today. Okay. And then your first 2 tests, if you turn those in, I've got them. I'll return them to you in the class. I returned them earlier, but I don't want to go through the stack every time someone goes in. Okay. All right, so you give me vector PQ in component form if you can. Or do whatever it takes to get to component form. How would you get component form? A little louder. Second? Yes. 2 minus 1 is 1. Continue. 3. 1 minus a minus 2 is 3. Negative 3. Okay? There's one vector. We're on section, in chapter 11, Vectors and Geometry of Space. 11.2 is Space Coordinates and Vectors in Space. We're on page 765, bottom of the page, example 5. Okay, there's one vector. QR. Okay, let's do vector QR. Okay, and what would it be? In vector components, 2, comma, 6, comma, negative 6. Okay, what you think? They are collinear. Why? Multiply that vector by 2 and you get that vector. Right? So yes, there is some constant c that the multiple of 1 of that constant times 1 will give you the other vector. So those are collinear. Now they, in the book, they did PQ, but then they did PR. Those are also collinear. Okay? So anyway, any one of those would have worked. Any questions? Let's go to example 6. Can I leave this up, or erase this, or does someone need it a little longer? Okay. All right. Example 6, top of page 766. Write the vector v is equal to 4i plus or minus 5k Okay, this is another component form, but this is using what I call the IJK form. It says write that in component form. So how would you write that in component form? Now notice it has a vector I and it has a vector k. What's missing? J. So this is obviously a three-dimensional vector. If that had been I and J, you couldn't tell if it's a two-dimensional or a three-dimensional vector. But with missing one, you know it has to be a three-dimensional. At least. It could be a four-dimensional, we just don't have but two dimensions. So let's do it as a three-dimensional vector. What would that be in component form? 4, comma, 0, comma, negative 5. That was real hard, wasn't it? Okay? The B part, that was A. The B part. Find the terminal point of the vector V is equal to 7i, this is a different problem, minus j plus 3k. And by the way, if you haven't noticed it yet, when I do a unit vector, I put the little caret on top, okay, the house top. The book doesn't do that, but I just find it useful. That way, when I look at it, I know I'm talking about a unit vector. And when you look at it, you know I'm talking about a unit vector. The regular vector, I put the arrow. The book bolds it, okay? They bold these too, but you can't tell the difference. But you know I, j, and k are unit vectors. Given that, okay, find the terminal point. So we're looking for the terminal point. Given that the initial point, P, is -2, 3, 5. Now, in case you missed it last time when we were talking about it, in this text, this author writes vectors in angle bracket notation, points in parentheses. Okay? If you see parentheses around a group of numbers, that means it's a point. Angle bracket means it's a vector. So if that's a point, that's a vector. That's a different kind of vector. Okay, it's a vector. It's just in IJK component notation. Okay, so we're looking for the terminal point. What you want to name the terminal point? Anything special? Make up a name. Q, why not? Okay, and that's going to be 3 values. Okay, now how do you get that? Okay, you can add, or I mean, if you want to think of this is Q1, Q2, and Q3. Those are the the coordinates of that point, and you know that Q1 minus a -2 has to be 7, right? That's how we did those. So therefore, Q1 must be, as you said, add those two. So what does that give you? 5. I'm going to erase all 3 of them since you already know the answer. Okay. 5. Second. -1 and 3. 2. Okay, I thought you were saying 6. I can't hear well. Okay. And 8. Okay. Let's just check and make sure. Okay. 5 minus a -2, sure enough, it's 7. 2 minus a 3 is a -1. 8 minus 5 is 3. Yes, that works. Okay? Not hard, was it? Let's do C. Find the magnitude of the vector V. I don't know why that vector symbol didn't show up. And this V is equal to -6i plus 2j minus 3k. Okay? Then find a unit vector in the direction of V. So the first thing they ask for is the magnitude of the vector V. Anyone remember what that symbology looks like? Double bars V. That means magnitude of V. Whereas V by itself with the bar over it, with the arrow over it, means it's a vector. When you put these around, it's no longer a vector, it's the length of the vector, so it's a scalar number. And how do you get that? Anyone remember? The square root of, second, the sum of the squares? Exactly. -6 squared plus 2 squared plus a negative 3 squared, which would be the square root of, second, 49. Okay, that's 36, and 4 is 49. Yeah, 49, and that is 7. So that is the magnitude of the vector v. But the second thing it asks for is find a unit vector in the direction of v. How would you do that? You want to give it a name? U, why not? But this U we're going to put with a hat over it because that's how I like to indicate it's a unit vector. It's in the direction of v, so I'm going to put it a sub v down here just to remind myself that's in the direction of v. How do we do that? Anyone? Second? Now that gives you its direction, okay? I want the component form of this unit vector v. Not u. In the direction of v. Anyone remember? Okay. All right. This vector v has a length of 7. So if we want a vector in the direction of v that has a length of 1, guess what we do? Divide by the length. Divide each component by the length. So that would be what? Negative 6/7 I plus 2/7 j minus 3/7 k. Or I would prefer to do it in component notation, but this is fine. Okay? And if you want to make sure enough, these are a multiple of that, so they have to be in the same direction, right? And if you took the square root of this squared plus that squared plus that squared, this would give you 36 49ths plus 4 49ths. It would be 40 49ths plus 9 49ths is 49 49ths, which is 1 unit vector in the same direction of v. Does that make sense? Way to remember that. Unit vector in the direction of v is vector v divided by the magnitude of v. Okay? That's the C part. All right, and if you notice, let's make sure they got the right answers too. The first A part was 4, 0, negative 5. Very good. Next one was Q would be 5, 2, 8. And the third part was magnitude was 7 and negative 6/7 I plus 2/7 j minus 3/7 k. Got it. All right, now. All right, for me to erase those. Bless you. All right. Now, example 7. It's measuring forces, or measuring force. A television camera weighing 120 pounds is supported by a tripod. Okay, I'm not going to draw it. Hopefully you've got it in your book. As shown in figure 11.23. Represent the force exerted on each leg of the tripod as a vector. Okay. Now, I almost have to draw it, don't I? Yeah. Okay. At least do a representation of it anyway. Here is like your x-axis. Here's something like your y-axis. And here's your z-axis. Okay? And by the way, those axes follow the right-hand rule when you point the fingers of your right hand in the direction of x and then bend them to the positive direction of y, you've got the positive direction of z with the right thumb. Okay? So that's a right-hand system we live in. Okay? Now, they tell you the camera's up here, and without drawing the camera, but just sort of doing something ugly like that, it's at position 004. Okay? Now, the weight of the camera they told you was 128 pounds, right? And that's a force vector straight down toward the center of the earth. So that's 120 pounds of force. Okay? It's supposed to be a B. Okay, 120 pounds of force. However, it's standing on tripods. Okay? The first leg of this tripod is over here, and mine is not to scale by any stretch of the imagination. Let me see if I can get it a little closer. Okay, this point here is 0, -1, 0. Okay, because -1 on the negative y-axis. The next point is here at √3/2, 1/2, 0. √3/2, 1/2, 0. I can't write. Okay, and the third leg is over here at -√3. Okay, -√3/2, 1/2, 0. Okay, now the question is, represent the force exerted on each leg of the tripod as a vector. Okay, and I guess this will be F1. Now these are not to scale either. This will be F2 and this will be F3. F3, I can't write. And these are all vectors as well. All right, Terrell, before you leave today, pick up two things. First, the first two tests, if you've turned those in already. And secondly, pick up your third test, which is your final exam, to turn in later this week. Okay? All right, so this is your representation. The big heavy camera, 120-pound camera sitting up there at 004, and then not to scale, those are the three legs of the tripod. Okay? Now, in reality, if you think of this, each unit on this z-axis is equivalent to, since it's 120 pounds downward, and this is 4 units up and 0 on x and y, each unit down here is representing 30 pounds, right? That's just a way to express it. I guess we lost somebody. I thought someone was coming in. Okay, we won't go there yet, but yeah, that's what we've got. Now, force F1, we may not know its magnitude yet, but we know its direction, don't we? Force 1, that's going to be, and they named these, they named P to be the vector up here, point P, not vector, point P. So let's clean this up a little bit and do it the way they do. Okay, this is point P, 0, 0, 4. Okay, this is point Q1 over here, I believe they call it. I should write that right in front of it. This one down here is Q2, and this over here is Q3. Okay, those are the 3 points. Now the force 1 down here, we'll represent that by what? What vector? If you know Q is this one and P is that one, what's the vector F1? Let me go and write it down. It'll be represented by PQ1. What vector would that be? 0, -1, -4. Okay, good. Okay, F2 would be represented by vector PQ2. Now, we aren't assigning any value to these numbers. They're just basically giving you the direction. And what's that? Square root of 3 over 2, 1/2, -4. Okay? And F3 is going to be PQ3, which is -√3 over 2, 1/2, -4. Okay. Now, what they didn't, okay. What they are assuming that you know, and I don't know if you know it or not, but each 3 of these legs are equal length. Now, obviously mine doesn't look like it, so therefore don't go by my picture, okay? But you can tell whether these are equal length or not. What's the length of this one? Anyone know how to get that? Length of that vector. How would you go about getting it? Anybody? What if I didn't call it length, but called it magnitude of the vector? Anybody? Square root of? What? Say again?
Yes, square and then add.
Yeah, okay. Square those and add them together. Take the square root, and what do you get? Square root of 17. That would be the length of that. How about this one? Well, let's do it easier. You see that all 3 of those are 4s, right? So let's do just some of the squares of these 2. That one's obviously what this one is. 3/4 plus, which is 1. And this is 3/4 plus 1/4 is 1. So yes, those are all the same length, and they're all root 17. That's the length. Okay. All right. So they are equal lengths. Okay. So, and the same force is distributed equally, but among the 3 legs. Okay. You know that each of those forces there is a constant that multiplying each one of those together, and then when you add the vectors, you've got to come up with something that's equivalent to 120 pounds. Okay? So, there's 2 things going on here now. We know that the sum of F1 plus F2 plus F3 is equal to F4. Is F. Okay, the weight of it. Yeah, that's just the weight. Okay? Now, we know what this F is. 0, 0, minus 4, right? Because its terminal point is down here at the base. Because if you use that to be the vector, when you add these 3 together, they've got to be that one down there. And since none of them have a component beyond that, they They can't. It's going to be I think that's a safe assumption. Okay? But actually, we know this is 120 pounds, and that's where I started with, so you know each unit is 30 downward. So your C here has to be 30, the thing that's multiplied together. And if you did a C1, CF1 plus C2F, CF2 plus CF3, that's going to give you CF, and C has to be 30, you can just go and multiply each of those by 30. Okay, so that would be 0, negative 30, negative 120. Whoops. No, that's not right. I'm sorry. That's not quite true. This statement right here is not, well, yuck. It's supposed to be erasing, and it's not erasing. There we go. Okay. But this does represent 120 pounds. Okay. So we know that each of these has a component of negative 40, and there are no other Z components, so the negative, they each have a negative 4, okay? And if you were to add those together, that gives you if you multiply, and wait, no wonder it's hard to read. All that writing has come down. Let me also erase this one because that's not, the eraser's not working. There we go. All right. I think what I said was so C times this plus C times that plus C times that. So here we would have that minus 12C is equal to, and that's your 120 pounds when you add each of those components together. So this gives you C is equal to C is equal to 10 because this is a minus 120. And where did I get K? I keep putting a K there rather than pounds. I don't know why that's happening today. It just is every time. Okay, 120 pounds. So, and that's downward, so that's a negative number. So C is equal to 10. So then your three vectors are 0, negative 10, negative 40. Oops, vector. (5√3), comma 5, comma negative 40. I did it again. And then negative 5√3, comma 5, comma negative 40. Okay. Quit. Okay. Now, I think obviously when you add these three together, 0 plus this will give you 0, which that one is. Negative 10 plus 5 plus 5, that gives you 0, which that one is. And negative 40, negative 40, negative 40, that's negative 120. Sure enough, that's what your total force is there. Okay? Now, so those are your three forces, F1, F2, and F3. I don't know. Wasn't a very satisfying example. It had potential, but it sure didn't turn out that way. Okay, let's look at homework exercises 11.2. You can do either 5 or 7 or both. They're both at calcchat.com. Neither are at CalcView. You can do either 9 or 11. They're both at CalcChat. 9's at CalcView. You can do any of the odds 13 to 23. They're all at CalcChat. None of them are at CalcView. Do 25 or 27 or both. They're both at CalcChat. The 25's at CalcView. Either 29 or 31. They're both at CalcChat. Neither are at CalcView. 33 or 35, they're both at CalcChat. 33's at CalcView. Any of the odds, 37 to 41, they're all at CalcChat. 39's at CalcView. 43 or 45, they're both at CalcChat. Neither are at CalcView. Do 47 is at CalcChat, but not at CalcView. Do 49 is at CalcChat, but not at CalcView. Do either 51 or 53, they're both at CalcChat. 51's at CalcView. Do 55 and 57, they're both at CalcChat. Either 59 or 61, they're both at CalcChat. 63 or 65, they're both at CalcChat, but 63 is at CalcView. 67 or 69, they're both at CalcChat. 67 is at CalcView. Do 71, it's at CalcChat, but not at CalcView. And any of 73 to 77, they're at CalcChat, but not at CalcView. Do 79 or 81 or both. 79's at CalcView, both of them are at CalcChat. Do either 83 or 85, they're both at CalcChat. Do 87, it's at CalcChat. 89's at CalcChat. There's a couple of writing ones so you can look at. Do whatever you want to with those, that's up to you. 95 is a using vector, which is a sort of a good application. 97 is a geometric application, which is a good one. 99 is another application, fairly similar to the one we did with the tripod, except now the base has the weight on it, not the top. Okay, so you can look at that one. 101 is another load support type problem, and 102 is a construction type. I'm sorry, 101 is a load support problem, and 103 is a geometry type problem. All right, let's move on to dot product. I was starting to do this when they said the force problem, thought they were going to do a dot product. I said, wait, we haven't done that yet. Now we're going to do the dot product, which will hopefully come back and have an application to forces. If I can get it to come up. Well, it's going to take its sweet time. Any questions on 11.2 while we're waiting for this to open? All right, here we are at 11.3. We'll start from the current slide. So we'll start from there. And again, chapter 11 is vectors and the geometry of space. 11.3 is dot product of two vectors. Now, are any of you familiar with dot products? Okay. In the old days, they also sometimes called it a scalar product because you multiply two vectors together and get a scalar number. But most times they don't use that terminology because you confuse that with multiplying a scalar times a vector, and they call that a scalar product. So in order to keep from being any more confusing than necessary, they just call this a dot product. Okay. Now, by the way, before you leave today, pick up your first and second test if you've already turned those in. You've already turned your paper in, but I can't return paper because they ask for samples of student writing periodically, so I have to keep those. And then also pick up your last test if you did not at the end of class. Okay, if you haven't already gotten it off the website, because William had asked me to put it out on Blackboard because he wouldn't be able to be here today, so I did that. All right. So the objectives here is use properties of the dot products of two vectors. Well, they first going to figure out what those properties are and then use them. We'll find the angle between two vectors using the dot product. We'll find the direction cosines of a vector in space. We'll find the projection of one vector onto another vector in space. And we'll use vectors to find the work done, there's the work, done by a constant force. That's what I was talking about earlier. So what in the world is a dot product? Now, we talked about vector addition and multiplication by a scalar, and by extension subtraction as well, which is just adding the opposite, so addition, subtraction are related, and multiplying a vector by a scalar. Now, each of these yields a new vector. What we haven't talked about is how to multiply vectors. And there's actually two ways to multiply vectors. One is called a dot product, the other called a cross product. And if you think about it, in algebra there are two symbols for multiplication. Well, there's actually maybe a third one if you want to think of it. A number written next to a variable or next to a parentheses is also multiplication. But when you use a symbol, you could use a center dot, which means multiply, or the good old X. We got away from using the X because that looks like the letter X, and once we got into algebra, you didn't want extra X's floating around, so we used dot product. Well, in vectors, those are different. Dot product is one kind of product, a cross product is another kind. We're going to focus right now on the dot product. This is your third vector operation, the dot product. This product yields a scalar rather than a vector. You multiply two vectors together and get a scalar. Whereas here, you multiply a scalar times a vector, you got a vector. Okay? Now you're going to multiply a vector times a vector and get a scalar. Okay? So here's the definition of the dot product. The dot product of this vector u, whose components are u1, u2. Now this is in 2 space. You could do it in 3 space or 17 space, but let's just keep this up with 2 space. Okay? The components of vector u are u1 and u2, and vector v are v1 and v2, just like normal. The dot product of these two is the product of the first components added to the product of the second components. And these components are not vectors, they're just numbers. So this is a product of two numbers added to a product of two numbers. That just gives you a number. In other words, a scalar. So the dot product of a three-dimensional vector, u1, u2, u3, and v, which is v1, v2, v3, is simply u dot v would then be u1, v1, plus u2, v2, plus u3, v3. So you can extend it to as many dimensions as you desire. Most of the time we're going to stay in 2 space or 3 space. Okay? That's how we define the dot product. Pretty simple definition. Product of two vectors giving you a scalar. Okay? Now, here are those properties of the dot product. Now we're going to have 3 vectors, u, v, and w. They're either in the plane or in space. And c is just a scalar. Here's the first. If you multiply to the dot product of u dot v, that's going to give you the same thing as v dot u. Okay? And that sort of makes sense because this is u1 v1 plus u2 v2. This is v1 u1 plus v2 u2. Okay? These are the same numbers. They're just multiplied and added in different order, but they're because addition is commutative of numbers and multiplication of numbers is commutative. The dot product is commutative. Okay? And associative. Oh, no, I'm sorry, distributive. Okay? And here's the distributive property. U dotted with the sum of v plus w. So this is the dot multiplication distributed over vector addition. Okay? This is u dot v plus v dot u. Well, think about this. U plus v, that is a vector. Dot a vector with a vector, you get a scalar. Here we have vector dotted with vector, which is scalar plus scalar. Sure enough, it's scalar. That doesn't prove the theorem, but it does show that it's at least consistent. Now here's an associative properties. Now you have to be careful, okay? This is a C times u dot v. That would be cu dot v plus u dot, which is also equal to u dot cv. So you can either associate the c with u and dot it with v, or associate the c with v and dot it with u. Either one of those, and you get the same result. Okay? So it's kind of a mix between a associative and commutative here because you're commuting the c. Now, this is one of those weird ones. The zero vector dotted with any vector v is going to be a scalar number 0 because this vector is 0, 0, 0. This is v1, v2, v3. 0 times v1 is 0 plus 0 times v2 is 0 plus 0 times v3 is 0, so that gives you the number 0. Now here's the interesting one. Well, they're all interesting, but this is even more so. V dot v, a vector dotted with itself. This will be v1, v1, or v1 squared plus v2 squared plus v3 squared. That sort of sounds familiar. That's the square root of those things, which is the magnitude of those things. This is the magnitude squared. So now we just have another way to get the magnitude of the vector. Dot the vector by itself and take the square root. That gives you a magnitude as well, which is exactly the same thing we were doing before. Just didn't call it that. Okay. That then leads to example 1. Let's do some of these. And here, believe it or not, is Elijah. Okay. There you are. Is your internship over? Oh, good. Welcome back. Okay. Here are 3 vectors. U, V, and W. Okay? First one, U is 2, -2, V is 5, 8, and W is -4, 3. Okay? What is the dot product of U and V? Okay. You multiply first component here over first component there, that gives you 10, and add it to the product of second by second. That would be -16. 10 plus -16 is +6. Okay? Well, they just did the first part for you. And the second part is 10 plus -16 is -6. Very good. Okay? How about that then times the W vector? This one here. Well, this would be -6, right? Times this will be, say again? 24, comma, -18. So that should give that to you. 24, comma, -18. C, okay? What would that be? U dot 2V. You can either do it the easy way or the hard way. How do you want to do it?
Multiply the V. Well, to make it easier, you just multiply the 2 to the other.
2 times -6. That's it. That gives you -12. Okay? That's the same as 2 times this. That we already know to be -6. So that would be 2 times -6 is -12. That's the easy way. We've got some lazy people in here. That's good. Okay? The D. what is W squared? The magnitude of W squared. How would you do that? W dot W, and that would be? That would be what?
-4 squared plus 3 squared.
Okay, -4 squared, which is 16, plus 9, which is? Okay, 25. So the square is 25. Okay, they'll get there in a minute. Okay, and by the way, just as before, magnitude is always a positive number, and of course magnitude squared is always a positive number. So if you ever get that to be negative, go back and change something because it can't be. Now what does that tell you? What is the length of W? 5, because this is that square. The magnitude itself would be the square root of 525, which may be the next example. No, it isn't. Notice the result of part B is a vector quantity. Why? Because you multiply a scalar times a vector and you get a vector. Whereas the results of the other three parts are scalar quantities because that was a dot product, and a dot product. Okay, and those are all scalar. It makes sense? All right. That was example 1. Now, there is another definition for what a dot product is. They haven't given it to us as a definition. I guess they're going to sort of come about it a different way. The angle between two non-zero vectors, because remember, a zero vector has no direction, so how can you have an angle between something with no direction? So the angle between two non-zero vectors is some angle theta. Now theta has always got to be between 0 and pi. Because the angle between a vector, this is an acute angle, a right angle, obtuse angle, a straight angle. You start going down here, the angle between those is obtuse again. So it's only between 0 and pi. Okay? Shown here. Here is the angle between vector u and vector v. All right. The next theorem shows how to find this angle using a dot product. So let's see, is there anything we can do here? Let's just go through the theorem. It would take too long to try to derive it from that. Okay? Angle between two vectors. If theta is the angle between two non-zero vectors u and v, and theta is between 0 and pi, then cosine theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Now this is not quite the way back when I first learned this, this was how it was given to me. And this to me, made more sense. Well, maybe it's because I learned it this way. They also gave us another definition of dot product, and here's what they gave us. Okay? That u dot v is equal to magnitude of u times the magnitude of v times the cosine of the angle in between. And that was just the definition. And obviously that is a scalar quantity, right? Magnitude of u is a scalar, magnitude of v is a scalar, and the cosine is a scalar. It's just a number between 0 and 1. Okay? The only thing wrong with that a little bit, no it isn't. Yeah, because u dot v can be negative, cosine can be negative as well, if it's between 0 and pi. It's positive between 0 and pi halves, and then negative between pi halves and pi. So yeah, that would be perfectly fine. They just take this and divide both sides by magnitude u by magnitude v, and that gives you cosine of theta. Know that in this theorem, that because magnitude of u and magnitude of v are always positive, u dot v and cosine theta, the same thing I was just saying, will always have the same sign. Okay? So the dot product of the two vectors will have the same sign as the cosine in between. Meaning if that dot product is negative, that means cosine that the angle theta is obtuse. If it's positive, the angle is acute. Acute angle, okay. So here are the possible orientations of the two vectors. For those who just came in or wondering, oh, I'm acting so strangely, I'm not acting. I really am strange. Maybe I didn't tell you all this, did I? About the weekend? Yeah, okay, yeah. I was mowing, it was Saturday, I think it was, down in a wooded type area, mowing downhill, and I happened to mow across a yellow jacket nest. They're underground, you know, and so I got attacked by yellow jackets while I was trying to get the lawnmower and myself back up the hill, rough, rocky terrain. I got stung at least 4 times that I know of, and then I have other itchy places. I'm not sure if they're mosquitoes or yellow jacket stings, but in the process of backing up, almost falling, doing all this stuff, I injured my knee again. I had injured it earlier in the term. I don't know if you remember that. And I was hobbling around some. Well, I re-injured it. So standing doesn't hurt. Sitting usually doesn't hurt. It's just changing the position is what hurts. So that's why I get that. Sit down and stand up really slowly. And steps are not fun either. Okay. But it shows the two possible orientations. When you and V are in opposite directions of each other, now you've got an angle of, how far is that angle? 180 degrees or pi radians. And what's the cosine of pi?
1.
Say again?
1.
Negative 1. So the angle, when the angle is pi, cosine of pi is -1. When you have, this is what I was just saying, when you have an obtuse angle here, the dot product is less than 0. They tell you that. They don't prove it to you, but you can see that because the cosine in the second quadrant, remember, all trig functions are positive in the first quadrant, only sine and its reciprocal, cosecant, is positive in the second, meaning cosine is negative. Only tangent and its reciprocal cotangent are positive, meaning sine and cosine are negative here. And over here, cosine would be positive, but we don't ever go over there. We are either acute or obtuse. If we're obtuse, this is a negative, so therefore the dot product has to be negative. Okay? Right angle, what's the cosine of 90 degrees, pi halves? 0. So two angles that are right angle with each other, the dot product is always 0. Hang on to that one, we'll hit that a little bit later. And if you're in the first quadrant, both angles are acute angle, the two vectors have acute angle in between. The dot product is positive because the cosine is positive in the first quadrant. And if they're in the same direction, guess what? U dot V, if they're in the same direction, the angle is 0, cosine of 0 is 1. That's when you get the maximum dot product, okay? The product between those two, magnitude of one times magnitude of the other times 1. Everything else, magnitude of this times magnitude of that times the number less than 1. It doesn't matter what the magnitude is, the product is going to be 0. Over here, magnitude of this times magnitude of that times the negative number, but it's still going to be less than -1. Here, the magnitude will still be in opposite directions, but the cosine is -1, so the dot product will be negative. Okay. From theorem 11.5, somewhere back there, you can see that two non-zero vectors meet at right angles if and only if the dot product is 0. Such two vectors are said to be orthogonal, 90 degrees. Okay. Why they have different names for them, I don't know, but this is very common, orthogonal. Okay, the definition of orthogonal vectors is vectors U and V are orthogonal if and only if U dot V is 0. So if you can multiply those two together, come up with a 0 dot product, you know the two vectors are perpendicular. Okay? So let's take a look at example 2. All right. I'm exaggerating things. It's not really as bad as it seems, but I just don't want to damage it any further, so I'm taking it very slowly. For U, 3, -1, 2, and V, -4, 0, 2, W, -1, -1, -2, Z, 2, 0, -1. Find the angle between each pair of vectors, U and V. How would we get the angle? Say again? U dot V. Okay, we'll do a U dot V. Will that give us an angle? No. Over the magnitude of U times the magnitude of V. Will that give us an angle? No, that gives us the cosine of an angle. So to get the angle, you would then do an inverse cosine. That gives you the angle theta. Okay? So, U dot V is not too hard to do. What would that give you? -12 plus 0 plus 4. That's equal to -8. We need to divide that by magnitude of U, which is going to be, say again? Okay. 314 is, oh, square root of 14. Okay, I was going to say that. Where'd you get that number? Yeah, 9 and 1 is 10 and 4. Yeah, so that would be the square root of 14. Okay, that's U, magnitude of U. Magnitude of V is?
Square root of 20.
Square root of 20. Okay, you could maybe simplify that a little bit, but that would be a -8 over the square root of, let's pull out a 4 out of that, and that would be 2 root 5. Okay, 2 root 5. And that would be 2 times the square root of 70, right? I'm not sure that's much better, but it was easier to do the math on it. And then punch that in on a calculator and take the inverse cosine of it. And I imagine they want you in radian notation, notation, so be sure you're in radian mode before you begin. Yeah, because you need to be between 0 and pi. What you get? Huh? Okay. Anyone got it yet? You're going to take the whatever number you get there and do an inverse cosine of that number. Second? 2.069. Now that is in radian notation. Where are you if you're an angle of 2 point something? Second quadrant, because remember pi halves would be about 1.5 something. This would be 3.141, stuff. So that would be something in between 1.5 and 3.14. So yeah. And this is Brendan. Okay. Okay, I can take it now. Got it. I don't need to fold it if you want to hang on to that. All right, dear, thanks. All right. Now, before I've said this to other people coming in, before you leave today, be sure that you pick up your first test because you just turned in the second in the paper, and also pick up the third test. Okay. And before you leave today, if y'all will stop me in time, I'll go over when I'll be available to receive your papers back. So I'll go over that again. So you're in the second quadrant, which you knew already because the cosine was negative and the dot product was negative. So we find the angle between each pair. We're in the second quadrant, 2.069 radians. Okay? How about between U and W? What would you do there? Again, your theta now, I'm going to put it theta UW, is going to be the inverse cosine of what? U dot W divided by magnitude of U times the magnitude of W. Okay. And what is the dot product of U and W? Second? Okay. 3 plus 1 is 4, minus 4 is 0. You're absolutely right. Okay. Now, what does that tell you? What is the angle? Theta is equal to? Second? I can't hear. Pi over 2, exactly. Okay. My hearing's so bad. Okay. Theta is pi halves. Those are perpendicular or orthogonal. So pi over 2. Without any calculation of magnitudes or anything else, you know that's got to be pi halves. So how about this is the A part, this is the B part. See if we can squeeze in C down here somewhere. V and Z. Oh, there's Z. Okay, I lost Z there. Okay, so the angle here between V and Z is the inverse cosine of V dot Z, I can't write, over magnitude of V times magnitude of Z. Okay. What is V dot Z? Negative 10, you said? Negative 10. That tells you what about these two angles? That's this angle. It's obtuse, yes, second quadrant. Okay? Inverse cosine. And what's your denominator? We don't need to do V. We already did that. Do you remember what it was? Was it that your root 20? Which is 2 root 5. And your magnitude of Z was, or is, or ever will be, root 5. Okay, so this is the inverse cosine of minus 10 over second. Okay, you're multiplying. Root 5 times root 5 is 5 times 2 is 10. And what's the cosine of negative 1? Inverse cosine of negative 1. Second? What angle would give you a cosine of? Yes. So theta is equal to pi. Okay. So, in other words, these two are, which we should have been able to tell if we had been paying close attention, these two are multiples of each other, so they're colinear, right? Negative 2 times this gives you that, right? So those are colinear, and sure enough, they're in the same direction. So let's clear what we've got here and see what we get. Okay. On the first one, cosine theta is U dot V over magnitude U times magnitude V. So that's negative 8 over 2 times root 70. I don't know why they wrote, yeah. Oh, when they factored out negative 4 over 70, root 70. Okay, and because that is a negative number, you have to be greater, you're an obtuse angle between pi halves and pi, and they got 2.069 radians, which is exactly what we did. Okay, the second one, u dot w, turns out being 0 over root 84. Who cares what the denominator is? It's 0. The dot product is 0. The angle, cosine of the angle is 0. That means the angle has to be pi halves. Okay? They are orthogonal, u and w. And then c, v dot z is minus 10. And the denominator is square root of 100. Some places they factor out, and some they don't. I don't know. Anyway, that's negative 10 over 10, which is negative 1, meaning the angle has to be pi. V and z are parallel, with v being negative 2 times z. Okay. All right. I noticed at least one person seemed like he needed to go, and why don't we take a quick break? I could sure use to get up and walk around a little bit. And we'll come back, try to keep it less than 5 minutes if possible. Okay. All right, we lost a bunch. That's sort of a disadvantage of having a break, I guess, but I think the advantages outweigh that, especially if you have to go. All right. So, this is what I was saying earlier. When the angle between two vectors is known, then you can rewrite theorem 11.5 as this. The dot product, number 4, we said was, how to calculate it. Now we can say, and this is what I said was how I learned it, magnitude of u times magnitude of v times the cosine of the angle in between. That's the alternative form of the dot product. Both of them are true, so since you know both of them are true, you can set one equal to the other. Produces an alternate way to calculate the dot product. Okay? Now, example 3, they're skipping, so let's us do example 3. Let's see if we can do it on the same page here. Okay? Given that the magnitude of u, which they didn't have to give it to us, they could just give us u, is equal to 10, okay? And the magnitude of v, that's pretty ugly. Okay. Is equal to 7. Okay. And the angle between u and v, I'm going to put angle theta between u and v is equal to pi fourths. Okay. Find u dot v. What would be u dot v? Pretty direct from our definition. Magnitude of u is? Anybody? Magnitude of u is? Anybody? 10, all right. Times magnitude of v is? 7. Times the cosine. What's cosine of pi fourths? Anyone know? several of you had better know. You were in my trig class. Pressure's on. Cosine of pi force. Cosine of pi force. Root 2 over 2. And 2 will go into 70 35 times, so this will be 35 times root 2, which is some number, whatever it happens to be. And that's how they leave it, 35 root 2. All right, any questions on that? Okay. Let's go to direction cosines. Okay. I always found this sort of strange to say this, but it's one way to express it. Okay. In space, it's convenient to measure the direction in terms of angles between two non-zero vectors v and the 3 unit vectors I, j, and k. Okay, as shown here. Here, and this is it's really hard to visualize this in 3 space. This vector is not in the plane yz. It looks like it could be, but it's not. It's sticking out this way, okay, from there, okay? So it's coming out this way. Now the direction cosine, direction angles, let's call it, the angle between the I vector, the unit vector in the I direction along the x-axis, that unit vector, and this vector v we're talking about, they give it the angle alpha. The one between the y coordinate, the j unit vector, and v is called the beta, and the one between the k unit vector and the vector v is called gamma. Now, those are called your direction angles. Okay. Just to give it to you. So anything in the first quadrant is going to have an alpha, beta, and a gamma, and I think I can safely say all 3 of those will be acute angles. None of them obtuse, because you're in the first quadrant, so all those angles will be less than pi halves or 90 degrees. Okay, the angles alpha, beta, and gamma are direction angles of v, and cosine alpha, cosine beta, and cosine gamma are direction cosines of v. Now, because v dot I, that angle v coming out here, dotted with the unit vector I, is magnitude of v times magnitude of I times the cosine of the alpha, the angle in between those two. Anyone tell me what magnitude of I is? Anybody? Magnitude of I. Say again? What do we just call I? What is I? Okay, it's along the x-axis. What else can you tell me about I? Say again?
I said additional. Additional.
Okay, I sometimes stands for that. This I doesn't. When we talk about I, J, and K, what do they stand for? The what? Okay, they're in the direction of X, Y, and Z, exactly. But what do they stand for? In that direction. I stands for the what did they name them here? The 3 vectors. Say again? Adjective. Unit vectors. What does that mean? What is a unit vector? Say again?
I said to angle.
No, okay. A unit vector. Did any of you ever play the card game Uno? No. You have. Okay. What does it mean? When do you yell out Uno? When you have one card left. Uno means one. So guess what that unit vector is? What? One.
One direction.
What's that?
One direction.
Okay, yeah. All vectors only have one direction.
One unit. One unit.
What is one unit?
One unit vector.
Okay. What is one?
Angle.
What two? Second?
Angle.
Okay. What two characteristics does every vector have?
Range.
Angle and a
Range.
magnitude. Well, obviously not an angle of one. One what? I mean, the angle is one. No. Its magnitude is one. Right? That's what a unit vector is. A vector whose length or magnitude is one. A unit vector. So, let's get back to this question here. Yes. It's by the definition, v dot I is magnitude of v times the magnitude of I times the cosine of the angle in between, which is alpha. What is the magnitude of I? Second? 1. All right. So this will just be magnitude of v times 1, which is 1, times the cosine of the angle in between. Okay? So, and in 3 dimensions, this will just be v dot I would be v1, v2, v3 times 1, 0, 0. So that would be v1 plus 0 plus 0. So that's just v1. So v, magnitude of v times the cosine of the alpha, the angle between it and the unit vector, is the component v1. It follows that cosine alpha is just v1 divided by the magnitude of v. Because this is v1, and that's also this. That equals that. v1 will be cosine alpha divided by the magnitude. Cosine alpha is v1 divided by the magnitude of v. Okay. So that gives you what that directional angle is, and the cosine of the directional angle. By similar reasoning, with the unit vectors I, j, and k, you have cosine alpha is the magnitude of in the v in the x direction divided by the component of v in the x direction divided by the magnitude of v. Cosine beta is the component v in the direction of the y vector, okay, times the y direction divided by the magnitude of v. And cosine gamma, the directional cosine between v and k will be v3 divided by the magnitude of v. So those are your cosine of those angles, and then taking the inverse cosine of them will give you the angles themselves. Okay, so consequently, for any non-zero vector v in space has a normalized form of v over magnitude of v. Remember, that's a unit vector in the direction of v, and that would be v1 over magnitude of vi, v2 over magnitude of vj, v3 over magnitude of vk, and that would be the cosine alpha I, cosine beta j, cosine gamma k. Because this is a unit vector, this follows a cosine squared alpha plus cosine squared beta plus cosine squared gamma has to equal 1, because this is a unit vector. Okay? Now, that leads to example 4. Goodness gracious. My wife said I needed to take some Advil today, and I thought it'd make me too tired. I'm beginning to think she was right, as she usually is. Okay. Find the direction cosines and the angle for which the vector v is 2i plus 3j plus 4k, and show that the sum of the squares of those, the cosines of those vectors are indeed, sorry, not vectors, the directional angles, the cosine of the directional angles squared is 1. We'll get to that in a minute. So, find the direction cosines. Remember how we did that? Cosine alpha is v1 over magnitude of v, right? So, what is cosine alpha? 2 over, what is the magnitude of v? Help me, somebody. Magnitude of v. Square root of what you say? 29. Okay. 16 plus 9 is 25, and 4 is 29. Perfect. Okay. There's your cosine alpha. What's cosine beta? 3 over root 29. You already did the hard part. Now it's just plugging in. And cosine gamma is what? 4 over root 29. Okay, those three out of Georgia. Never mind. Okay. So there are your three cosine, direction cosines, and the angles. So I guess we need to do the angles too. Alpha would be equal to the inverse cosine of 2 over 29. You'll need your calculator for that one. 2 over root 29. Anybody? Give it to me, I'm pretty sure in radians is what they want. No, they want it in degrees. Amazing. So be in degree mode. Sorry about that. Anybody? 68.2 degrees. Excellent. All right. How about beta? $56.1 degrees. Is that what you said? Close enough. Okay. And gamma? 42.0 degrees. All right. Now, the last thing it says is to show that the sum of the squares of those direction cosines is equal to 1. Well, I know what this one would be. That would be 4 over 29 plus 9 over 29 plus 16 over 29. And sure enough, that's going to be 1629 over 29, which is 1. Absolutely. A lot like your components of a unit vector always have to be 1. Components of your direction cosine squared have to be 1. Yes? I thought they wanted it in radians, but then they gave their answers in the book in degrees, so I said do it in degrees. But if you do radians, it works too. I was surprised. I was expecting to see radians, and they did degrees. Okay. Oh, let's see how they did the problem. I'm running out of juice really fast here. Okay. Because magnitude of v is square root of 2 squared plus 3 squared plus 4 squared, the square root of 29, you can write the following. Cosine alpha is equal to 2 over root 29 cosine. Oh, and then they went on and calculated it by doing the inverse cosine of it. And that gave you alpha is 68.2 degrees. Cosine beta is V2 over root 29. That is 3 over root 29. That gives you beta equal 56.1 degrees. And cosine gamma is equal to V3, which is 4 over root 29. And that would give you gamma equal 42.0 degrees. Okay. Furthermore, the sum of the squares of those direction cosines are 4 over 29 plus 9 over 29 plus 16 over 29, which certainly adds to be 29 over 29, which is 1. Okay. Oh, all right. And here's basically how this works. You're going 2 units in the I direction, 3 units in the J direction, and 4 units up in the K direction. It seems a little bizarre now. Here's your angle alpha, your angle beta, and your angle gamma. And those are direction angles. And the cosines of those are your direction cosines. Okay, that's example 4. All right, now let's talk about projections and vector components. How are we doing? We got time. Okay. You've already seen applications in which 2 vectors are added to produce a resultant vector. Yeah, we added 2 vectors many times. Many applications in physics and engineering pose a reverse problem, decomposing a vector into the sum of vector components. Okay? So when we add 2 vectors, you add the individual components, but let's do it the other way. The following physical example enables you to see the usefulness of this procedure. Okay? Here we have a boat on an inclined ramp, and the force due to gravity pulls the boat downward. Okay? The ramp, down the ramp, and against the ramp, because the force on the boat due to gravity is straight down, but the ramp is slanted. So one component of this force is perpendicular, that's against the ramp. The other component is pulling it down the ramp. That's why you have to exert a force to not keep it, well, to keep it from even rolling backwards. You have to exert a force. Okay, these 2 forces, W1, this one, and W2 there, are orthogonal to each other, and they're called the vector components of F relative to the plane. Okay? Now, this is just the physicist in me. I call this W parallel and W perpendicular. Because this is parallel to the ramp, that's perpendicular to the ramp. Okay? And that, to me, is the easy way to think of it. W1 and W2 are fine, but they don't tell you very much. The force here, and the reason they're using W's is that's the weight. The weight is the force of the earth pulling down on the boat and trailer. Okay? So that's why the total weight, or the force downward, is the weight parallel to the ramp and the weight perpendicular to the ramp. Vector components of F. The forces W1 and W2 help you analyze the effect of gravity on the boat. For example, W1 indicates the force necessary to keep the boat from rolling down the ramp, whereas W2 indicates the force that the tires must withstand in order to push. It's called the normal force. That's the gravity pulling down, so that's the force which the tires have to be pushing against the ramp. Okay? Jump into definition of projection and vector components. Is that all they did with that? No, okay, yeah, that's all they did with there. Later they're going to do a problem with that. Okay, I want to make sure they did that now. So here's the definition of projection and vector components. Let U and V be non-zero vectors. Of course, it doesn't work when it's a zero vector. That's why I don't even like zero vectors. They're not really like vectors at all. Moreover, let U equal W1 plus W2. Okay? Where W1 is parallel to V and W2 is orthogonal to V, as shown in this figure here. Here is V in the direction of W1, okay, parallel to that, and W2 is perpendicular to V. Okay. W1 is called the projection of U onto V. Okay? Even though V doesn't extend that far, it's still the projection of U onto V. In fact, I would say, just looking at this and making an estimate, W1 would be 2 times V. It's in the same direction as V, but twice the magnitude. That's beside the point here. Projection of U onto V, or the vector component of U along V, and is denoted by W1 as projection in the direction of V of the vector U. Okay? W2 then would be U minus W1, because W1 plus W2 is equal to U, so W2 would be U minus W1, okay? Which is called the vector component of U orthogonal to V, okay? Or perpendicular to V. Okay? Now, that's when theta is obtuse, is acute. That was this picture. When it's obtuse, the component of U that is parallel to V is now actually a negative component because it's an obtuse angle. And the adjacent side of an obtuse angle is this side over here. It's in the opposite direction, so it's a negative. W2, though, is still positive because you're either acute or obtuse, so W is always going to be the vector component orthogonal to V. That's positive. Okay. Now, here's example 5, bottom of page 774. Okay. Find the vector component of U orthogonal to V. Find the vector component of U, which is 5, 10, those are components, that is orthogonal to V, which is 4, 3, given that W1 is projection of, in the direction of V of U, and why would they do that to you? Okay. All right. Boy, they give you way too much here, don't they? Well, they sort of have to because they haven't given you the theorem yet or the definition yet. So I guess they had to do this. Now, why didn't they give you this first? Okay, this is what they should have done, I think. Okay, here is vector u. It's in 2 space, so xy plane, not 3 space. U is 5, 10, and they drew it from the origin, so u could be written as angle bracket 5, 10, or terminal point 5, 10 written as a point. Okay, where v is 4, 3. Okay, now what they show here is the projection of u onto v would then be this part here, which is 8, 6, which is exactly 2 times 4, 3. So you see it is a projection onto 4, 3. It's just twice the length of v. Okay, so that's your W1. Okay, with that in mind, then W1 plus W2 has to equal U. Okay, so in other words, U minus W1 is equal to this, so let's do that. 5 minus an 8 is 5 minus 8, negative 3, and 10 minus 6, 4, negative 3, 4. Sure enough, this completes the rectangle there. I want to say parallelogram, but these are actually rectangles because those are right angles. Okay? And there you have it. But they just told you what that 8, 6 was. They didn't. And that to me, that to me made it a bit strange that W1 is projection of U onto V, which is 8, 6. They didn't show you how to get it. That's going to be the next theorem. U is 5, 10, and W1 plus W2 has to equal U, so therefore W2 is U minus W1, so negative 3, 4. Because U, is equal to that, W1 parallel to V, it follows that W2 is a vector component of U orthogonal to V, so that's what we're looking for. That was negative 3, 4. There's your picture solution. All right. I'm getting hungry. Okay. The granola bar ran out a while back. Okay, here's theorem 11.6. Projection using the dot product. Oh, no wonder it came up in this section. That's using the dot product. If U and V are non-zero vectors, they've got to be. You never mess around with zero vectors. Then the projection of U onto V is, here's the definition, U dot V, there's your dot product, divided by V prime, V, magnitude of V squared, V prime comes up, times V. Okay? Now, they just give that to you without any other thing. But let's see if that kind of makes sense. Okay? And this is just a generic kind of thing. Projection of U in the direction of V. Well, obviously, it has to be in the direction of V, so it has to be some multiple of V. And this, of course, is just going to be a scalar, because U dot V is a scalar, and V magnitude squared is a scalar. So this is the thing that multiplies by V that gives you the projection of U onto V. So at least the direction's right. Okay? Now let's see if the magnitude looks like it's right. Now this is not precise by any means, but it just at least gives me the idea that I'm in the right direction. This kind of looks like a V times V here, doesn't it? It's not, but it kind of looks like this. Divided by magnitude squared, that sort of feels like that ought to be 1, and 1 times U is U. So that's projection, but it's projection in the direction of V. Now that just is a feel-good type thing there. The book doesn't go into that. The projection of U onto V can be written as a scalar multiple of a unit vector in the direction of V. Well, What's the unit vector? Basically, v dot v over magnitude of v squared. That's what it is, okay? So, what they do is do the u dot v over magnitude v squared. Let's split this into magnitude of v here times magnitude of v there. That's magnitude of v squared. Okay, well, v over magnitude of v is the unit vector in this direction of v, right? So this is a scalar quantity, scalar over scalar. U dot v is a scalar, magnitude of v is a scalar, and this is some constant times that unit vector. And that constant is u dot v over magnitude of v. Okay? Which, if you think of this is u of dot v over v. There's a unit vector. I mean, there is a unit vector again, and that just be u times the cosine of theta. Okay, where did that come from? Wait. Magnitude of v. Magnitude of u. Remember from the definition of the dot products that u dot v is magnitude of u times magnitude of v times cosine of the angle theta. So divide by magnitude of v, and that gives you this. That part is your k. That is magnitude of u times cosine of theta. So, bunches of relationships can show up here. It's just keeping them all straight. The scalar k is called the component of u in the direction of v. So in other words, how many times has u been scaled up or down from that unit vector v? Okay? And if k is a large positive number, it means you're several times larger. If it's a number less than 1, then that means it's a smaller scaling. You're scaled down from the unit vector. Okay, example 6. Find the projection of u onto v and the vector component of u orthogonal to v for this vector u. Oh, and that vector v. U is 3i minus 5j plus 2k, and v is 7i plus j minus 2k. Find the projection of u onto v and the vector component of u orthogonal to v. Okay? Let's start with the projection of u onto v. Do you remember how that goes? Projection of u onto v is equal to what? Do you remember? You just had it. There's your definition right there. U dot v over v magnitude of v squared times the vector v. U dot v onto goodness gracious, I can't write. Okay. Magnitude of v squared times v. Okay. So let's take it a step at a time. What's u dot v? Anybody? U dot v. Say again?
You have to multiply it, right?
Yep.
It's 21i.
Okay, you don't use vectors anymore. It's going to be a scalar. 21.
5. Well, -5.
Okay, that would be a 16.
How?
You're adding them.
Oh, yeah.
Yeah.
Sorry. You're good.
21 minus 5 would be 16.
16.
Minus 4.
Oh, yeah. Sorry, I was adding them again.
Okay. 16 minus 4 is
12.
12. So the U dot V is 12 over magnitude of V squared. What would that be? $49 plus 1 plus 4 equal 54. Is that what you said? Okay, 54. Okay, in the direction of V. Well, let's simplify this a little bit. I know 2 will go into each of that. 6. Well, I know 6 will go into that. Okay. 6 will go into 12 twice. 6 will go into 54 9 times. Okay. Oh, goodness gracious. So that's 2 nights times V. So that will be 14 nights I plus 2 nights J minus 4 nights K. So that's projection of U onto V. Okay. Now, the second part says the vector component of U orthogonal to V. Okay? Now, remember the relationship between the projection of U onto V and the component of U orthogonal to V. What do those two have to add up to? Not 1. Let's go back. Right here. They add up to U. This is the projection of U onto V. There's U. So the projection, the orthogonal component of U with V onto V is the sum of these two have to add up to U. So the difference of that and that has to be W2. So, so I'm going to call it U orthogonal, okay, to V, okay? So that's going to be U minus this. So 3 minus 14 nights. Well, 3 is 27 nights, right? Minus 14 nights would be 13 nights I. Minus, I think it's going to be, because it's 45 nights minus 2 nights, a negative 45 nights minus 2 nights would be a negative 47 nights J, and uh, 2K that would be 18 nights minus a minus, which is plus 4 okay, 18 nights plus 4 nights would be 22 nights. Okay, that I think is the projection. They call it W1. I like to call it U perpendicular to V. It's an ugly V down there. But let's see what they got. 13 nights I minus 47 nights J plus 22 nights K. Good for them. Okay, and the projection was 14 nights I plus 2 nights J minus 4 nights K. All right, let's clear our scratch and see how they do it. We're running out of time, sorry. Okay, projection of U onto V is exactly like we did, and they call it W1. U dot V over V squared, magnitude squared, times V, and that would be 12/54, which is the same as 2 nights times 7 would be 14 nights I plus 2 nights J minus 4 nights K. Okay, vector component of U orthogonal to V is W2 is U minus W1, which would be 3I minus 5J plus 2K minus 14 nights I plus 2 nights J minus 4 nights K. And I like to go on and change this to nights. 27 minus 14 is 13 nights. 45 minus 2 is negative 47 nights. And 18 minus a minus, which is plus 4, is 22K. So here's the figure of that one. Boy, talk about a confusing looking graph. That's what makes it so difficult doing three-dimensional drawings on a two-dimensional board. Here is U1, which is your 3I, so in the, okay, here's your orientation. Here's your X, there's your positive Y, and here's your Z. So, well, it's hard even to visualize. I guess like that would be better. Okay? Now, it's positive 3 in the X direction. 2, 4, 6, 8. So 3 would be right here, and project this that way. That doesn't, no, I'm sorry. Project this way. Parallel to that, coming here. It still doesn't look right, but that's 3I minus 5J. Well, here's 2, there's minus 2, minus 4, minus 5 would be back here. There's your minus 5J. And plus 2K, and you go up from here. So you first are projecting onto this, and then this, and then up. Okay? So there's your U. Projection of that onto V, which they don't show here. Here they do. 7I, so that's up here. Come across here, there's 7I. Plus J, just 1 on the J, that would be here. Okay, that doesn't look like it's in the right place, but let's assume that it is. And then minus 2K, so it's going down K units here, and there's your V. Projection of this onto that is a pretty small number. This one. 14 nights, that's less than 1, not even less than 2, between 1 and 2, here, that would be 1 unit, so less than 2 units this way. And then a very small j, 2 ninths of a j, and then that's supposed to be 4 ninths. I don't know what happened to the 9 there. K. So it's just up, no, minus 4 ninths, just a little bit down from there. And there is your projection of U onto V, and then that's your W1. W2 would be the other component of this perpendicular to that. So this minus that is that. That's what they have here. 13 ninths U. So this would be a little less than 1. It's so hard to see this here, but sure enough, it is. It's just slightly this way. Minus 49, 7 ninths, so that's more than 5. And this is 2, 4, 6. So something here. So again, it's really hard to see how this fits. And then 22K, max K, that's a little bit more than 2, 2.5. So something here, and that would be the K component. Really, really hard to visualize this in 3 dimensions on a 2-dimensional plot. Okay, I think we have almost done all we can, and we didn't get to work. Okay, sorry about that. Well, also there was a example 7, finding a force, and we didn't get to do that one either before we get to work. Homework exercises here, if you do need to go back and do them and to follow up on it. Any of the odds 3 through 9, they're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. Do number 19, it's at both of them, Calc Chat and Calc View. Any of the odds 21 through 25, they're all at Calc Chat, not at Calc View. 27, 29 are at Calc Chat, but not Calc View. Any of the odds 31 to 35, all at Calc Chat. 31's at Calc View. 37 to 43, all at Calc Chat. 37 at Calc View. And 49 is a Calc Chat, 51 or 53 is a Calc Chat, 55 or 57, and there you may be getting into where we didn't get to do, so stop somewhere there. Sorry, we didn't get to do cross product. Now, is anyone here who did not pick up test 3 yet? Okay. Anyone who has not turned in your test 1 and test 2 yet? Okay, I need those as soon as you can get them to me. Okay, and here's your test 3. Now, if all of you get out your test 3 for just a moment.
You can see the section first, right?
What's that?
You can see which section goes to what?
I can't hear you.
So you can see what section goes to.
Yeah, that's what I'm going to do. Could you say that right here? Okay. Here's your test 3, and there's your test 3. Okay. Now, let's see if I can get these things so I don't lose where I am. All right. I need my books. Okay. Just too crowded here. Okay. All right, question number 1 is from section 9.1. Question number 2 is from 9.2. Question number 3 is from 10.2. I believe it is. I believe that's right. Question number 4 is from 10.3. 4 and 5 are from 10.3.
Question number 3 was from
2. Okay. Question number 1 was 9.1. Question number 2 is 9.2. Question number 3 is 10.2. Questions 4 and 5 are from 10.3. Question number 6 is from 10-4. Question number 7 is from 11-1. Question number 8 is from 11-2. Question number 9 is from 11-3. And number 10 is from 11-5 that we didn't get to do. No, 11-4, which we didn't get to do. So if you, number 10 is completely optional. If you want to give it a shot, you get it right, you get a bonus point. If you don't get it right, you don't lose anything. If you leave it blank, you don't lose anything.
I already tried it.
Huh?
I already tried it.
Okay. Number 10 is from 11-4, but we didn't get to go over it, so that's completely bonus. Completely bonus. So I'll only be grading 1 through 9 for credit, and 10 will be a bonus if you get it right. If you don't get it right or don't even try it, it doesn't lose you anything. Okay. Good deal. One more thing, folks. Have everybody done these student course evaluations? If not, please do them. Please do them. Okay. All right. Good deal. I'll look forward to seeing you sometime this week, Monday, Tuesday. Oh, I didn't get to go over where I'll be, did I? Okay. Let me go over that quickly with you. I think I'm in the right place here. I hope so. Nope, I'm not. Okay. Today I'm on campus all day today until 6 o'clock. No more classes today. Tomorrow, in my office, that's room 265, from 7:45 in the morning or thereabouts until noon. At noon, I've got a final in this room from noon till 2. If you want to turn it in then, and you don't want to bother the class, which wouldn't be a big bother, you can just slide it under my door. Okay, from 2 until 3:30 tomorrow, in my office, 265, I don't know where that came from, 265, and then at 3:30 I have to leave to go to the Birmingham East Campus. I'll be there from 4 to 6. Birmingham East Campus is Ethel Hall Health Professions Building, and it's an L-shaped building. When you walk in the vertex, hang a left, and go right past the restrooms, and the first classroom on the left is 103. That's where I usually stay. Okay, and that's tomorrow. Wednesday, I'm here all day long, 7:45 in the morning until 6 o'clock in the evening, in or around my office. Okay, and then at Thursday, here all day long, 7:45 until 3:30. At 3:30, I go to Birmingham, and I'm there from 4 to 6. Okay. Friday, the college is still not open, even though it's going to be August. The college is not open on Friday, so don't try to bring anything that day. Monday grades are due at noon on Monday. So meaning if I don't have something in when I walk into the office and can grade it right then, like if you want to turn in something Thursday afternoon, I've already gone to Birmingham, slide it under my door, and I'll pick it up first thing Monday morning. But if I don't have it by then, I probably won't have a chance to get it graded. You're going to get an I, and as soon as I can grade it, then I'll change the I to a letter grade. Okay? And I won't be here past Monday. If you turn it in to me, slide it on my door Tuesday or Wednesday or something like that, I won't see it until I get back on campus fall term. So the I will remain until I can get it graded and change the grade. So try to get everything in. Oh, wait, who is this? I think I've seen him somewhere before. Okay. All right, and let me see. Oh, yeah, you did it. Okay. The other thing, though, did I return your other test to you? What's that? Yeah. Okay.
Oh, you did. Yeah.
Let me see if I've got these back in any kind of order at all. Oh, there's test 2. Good. Jeremy. Test 1. Okay, you just gave me test 2, and you gave me your research paper, right? 2.
I told you that. Bro, it was something else, bro. Oh, yeah.
All right.